Hey guys, so today what we're talking about is average atomic mass. All this is that it's a math calculation and it deals with the isotopes of certain elements. What you're pretty much going to be finding is that scientists a long time ago wanted to figure out what the molar masses of the elements on the periodic table were, and they were able to figure that out, as you can see from these numbers underneath each of these elements. Okay, those are the average atomic masses. Well, how did scientists figure this out? Well, what they did is that they looked at isotopes of the elements, right? Isotopes are elements with the same protons but different neutrons. Examples of this are things like carbon 12, carbon 13, and carbon 14, right? Same protons, different neutrons. And they show up in different abundances. Carbon 12 might show up, might be 90% abundance. It might be the most common carbon atom you see. 13 might be 8% abundant, and then 14 might make up the last 2%. So what they do is they take the average atomic mass out of these based on their abundance. It's based off of this one formula. So, and that is, let me erase this. If I can find my eraser, there it is. So this is the one formula that you can write on your periodic table that we're going to be using for average atomic mass. Average atomic mass equals the mass number of isotope 1 times the percent abundance of isotope 1, okay, plus the mass number of isotope 2 times percent abundance of isotope 2, and so on and so forth for however many isotopes you have. In this case, we have 3 isotopes. So this is not accurate in the real world of the percent abundance of these isotopes, but let's just go ahead and solve these anyway, right? I might say, what's the average atomic mass of carbon given all these isotopes and their percent abundances? Okay, so what I'll do is I'm trying to figure out average atomic mass. For the first isotope, I want the mass number. Mass number is this guy in the upper left, right? So that mass number is 12. And I'm going to multiply it by its percent abundance, but the percent abundance is not going to be in the percent form, it's going to be in its decimal form, right? So to get something from its percent form to its decimal form, we just move the decimal left 2. So 90% is actually 0.90. If we looked at 8% and move the decimal left 2, okay, it'd be 0.08. If we looked at 2%, we move the decimal left 2, it would be 0.02. Okay, and that's what we're going to put in for those percent abundances. So for this isotope, the percent abundance is 0.9. And then we're going to do that for the second isotope as well. So plus the mass number of isotope 2 is 13. The percent abundance is 0.08, right? Because we changed that percentage to a decimal. And then for the last isotope, we'll take its mass number times its percent abundance, which in decimal form is 0.02. Alright, and then we'll add those up in the handy dandy calculator. Again, this isn't a real representation of carbon's isotopes. This was just an example I came up with off the top of my head, but let's see how close it actually is in the old calculator. 14 times 0.02. And I ended up with an average atomic mass of 12.12. And the units for average atomic mass, if you remember from molar mass, it was grams per mole. Okay, so that's how we'd get our answer. Again, this is not accurate. If you look at the average atomic mass for carbon on here, it's actually 12.01. So my made up example was not accurate, okay? So again, they want you to know how to go through this process, how to figure out how these scientists figure out these average atomic masses, and let's go ahead and let's do a few more examples. So, there will be a situation where they won't give you a nice rounded mass number like 12, 13, or 14. They may give you a more specific one. And let's go ahead and do that right now. So let's calculate the average atomic mass of silicon. Okay, average atomic mass of silicon, and I'm going to give you a little table here. We got silicon 28, we got silicon 29, and we got silicon 30, okay? And then I'm going to put mass in this column and percent abundance in this column. This one's going to be 27.98, this one is going to be 29.02, and this one's going to be 29.98. With percent abundances of 92.23%, 4.77%, and 3.00%. Now, as I said last time, we had nice rounded mass numbers of 12, 13, 14. This time, they give you some more, they give you both actually. They give you 28, 29, 30, and then they give you these more specific mass numbers, okay? Always use the more specific mass number if they give it to you, okay? If they don't give it to you, then you can go ahead and use these rounded answers. But if they give you a more specific mass number, go ahead and use those in your calculations instead. So, we want average atomic mass. We have mass numbers in our percent abundances, so we just plug this into our little formula that we got going. So we want average atomic mass. We'll go mass number of isotope 1, which is 27.98, multiplied by percent abundance. Remember, we move that decimal to the left twice. Don't forget that. That's the biggest mistake that people make with these. So we move the decimal to the left twice. It'll be 0.9223. Do the same thing with the second isotope, which is 29.02. Multiply by its percent abundance. Again, we move the decimal. We move the decimal to the left twice. 1, 2. So it will be 0.0477 plus our last isotope. These are multiplication signs, by the way, if you can see them. And then the last one, the mass number is 29.98. And its percent abundance is 12.0300. Okay? So we go ahead and we add all those up into the old calculator of 27.98 times 0.9223 plus 29.02 times 0.0477 plus 29.98 times 0.03, and you should get something around, I'll put it right here, I got 28.0, let's just go with 1.6. Well, let's do significant figures, 1.02. Okay, grams per mole. We'll stay consistent with these 4 sig figs that we're having. That one has 3, that one has 3. We'll just stick with 4 for now, okay? That's specific enough, 28.02. All right, let's do another example. Let's do one where we're missing something else, like a percent abundance, all right? So, I will give you both mass numbers, and what you'll be missing is, or I'll give you both percent abundances, and what you'll be missing is a mass number. So let's figure that out. Let's say this is example 4 in my notebook. We'll just say it's example whatever for us. Rubidium has 2 isotopes. let me actually throw a little bit of a curveball at you. We got rubidium 85, which we'll say is at 72.2% abundant. And we'll have rubidium Y, which is at a certain percent abundance that we don't know. And the average atomic mass of rubidium. If you never know what the average atomic mass, or I don't give you the average atomic mass, and I'm asking for like mass number percent abundance, you could just look on the periodic table, okay? So for rubidium, it's 85.47 is good enough for me. Okay, so average atomic mass is going to equal 85.47 grams per mole. Okay? And some of you might be asking, Mr. Dahmer, why are we doing this if the answers are just on the periodic table, if the average atomic masses are on the periodic table? It's good to know how to do these things, okay? And most of the time, you're not going to be solving for average atomic mass. You're going to be solving for, like, mass number or percent abundance, okay? And I will make the answers so they're not exact to the periodic table. So make sure you're showing your work so that I can see that you're doing the right answer, okay? Let's go ahead and let's solve this guy, okay? So I am going to need mass number of isotope 2 and percent abundance of isotope 2. That's what I'm trying to figure out. First thing, I can figure out the percent abundance pretty easily, okay? I don't need to do any crazy calculation. I just know that out of these two isotopes, they should make up 100%, right? It should make up all the isotopes, so it should make up the 100% of them. Well, if this isotope makes up 72.2%, how much is this guy going to make up? The remainder to 100%. So, if I know the total has to be 100%, I'll just subtract 72.2%, and what's left over should be 27.8%. Okay? So, I know that my remaining percent abundance should be 27.8%. Okay? So that's an easy way to figure it out if you just have two isotopes. Mass number, I don't know. That's where we got to use our formula that I gave you earlier. Okay, so average atomic mass we know is 85.47. Okay, mass number of isotope 1 is 85. I didn't give you anything more specific, so you could just use 85. Percent abundance is 0.722. Mass number for this one we don't know. We'll label it as Y times percent abundance 0.278. Okay, now we're just getting into some algebra. Let's go ahead and let's simplify where we can. Okay, this is as simplified as it'll go. I can simplify that, right? I can multiply those two, and I could take 85 times 0.722 and get 61.37. And this guy, I could simplify into an algebraic expression, right? Y times 0.278. If I multiply those together, it's just 0.278 Y. Now it's a combine like terms situation. All right, so these guys are just constants, so let's go ahead and subtract those to combine them. And we want them on opposite sides. So then I'll take 85.47 minus 61.37. And I'm going to erase this and go up here since I'm running out of room. I'll get 24.1 from down here equals just my 0.278y. Get y by itself, so let's divide by 0.278. Divide by 0.278. That cancels out. And my mass number should be 86.69. Okay, 86.69. So that's good enough for me. Okay, if you want to round up to 87, that's okay. But 86.69 mass number, no units there. Okay, it's just 86.69. Let's do one more like that, and I'll leave it up to you, and I'm done. So let's do another situation just like that one. I'll create a nice little table. All right, we'll have isotope. We'll have percent abundance, and we'll have mass number. Okay, I have potassium 39 with percent abundance 93.12%. I don't have the mass number. I have potassium 41. I don't have a percent abundance there, but I do have a specific mass number of 40.962. And I want you to calculate, this is a question mark, I know that looks goofy. I want you to calculate percent abundance and mass number, okay? Well, let's start off with the easy stuff, right? I could do percent abundance pretty easily. It's out of 100%. If this makes up 93.12%, this must make up the remainder to 100%. So, I'll do 100% minus 93.12%. And I should get 6.88%. Okay, easy. That one's not bad. Mass number, okay, we gotta do a little calculation here. We need to use that average atomic mass equation. But wait a second, Mr. Dahmer, you didn't give me the average atomic mass for potassium. Well, remember, if I don't give you the average atomic mass, you could always find it on the periodic table. Okay, so in this instance, we could use 39.1 as our average atomic mass for potassium. Okay, so again, if you're missing a variable, you could either get it from the periodic table for average atomic mass, or you could get the percent abundance because it's out of 100. All right. So here, let's go ahead and plug in what we know. For isotope 1, we don't know the mass number, right? We're looking for the more specific one. So I'll just put a Y right there. I do know its percent abundance is 0.9312. For isotope 2, I do know the mass number to be 40.962. Percent abundance, I move that decimal left twice to make it 0.0688. And it looks like from here, it's just some algebra, alright? This is as simplified as it can go. This becomes 0.9312y. Second one becomes 40.962 times 0.0688, which equals 2.82. Time to combine like terms, and I'm going to go, I'll stay down here. I'm going to subtract 2.82 from both sides. So 39.1 minus 2.82 equals 36.28. I'm going to move it over here. Equals 0.9312y. Okay. So I've subtracted those, got 36.28. Divide by 0.9312. Divide by 0.9312. And you should get a mass number of 38.96. So that is our mass number. Okay? Again, pretty much just a plug and chug calculation. Remember to move those decimal places to the left when you're dealing with changing percent back to decimal. And that's it, guys. Have yourselves a great day.